and design this scaffolding with an A36 standard steel pipe and medium heavy duty construction. That means the load is going to be 50 pounds per square foot, and the scaffolding we're going to design is going to be 3-level, and the scaffold with the front to back is the width of it is going to be 4 feet. The distance between the posts along the front and back is 7 feet, so it's 7 feet span. And then distance between level is 9 feet, so 3 times 9 is 27 feet tall. Now the planking for the scaffolding is a Douglas Fair construction grade, which let's use FB is equal 1000 psi, and then A36 steel. You all know the your bending stress is going to be 36,000 psi. That's a Schedule 40. So one of the first thing we're going to do is we're going to design the scaffolding, and if you look at the scaffolding, the planking, and we're going to say it's 7 feet. It is 7 feet wide, and we'd like to know the load on top of it. It's a medium heavy duty. That means it's designed for 50 pounds per square foot, or we can say pound per square foot. All right. So now we have that, and I want to convert this to a pound per foot. So I'm going to take multiply by turbo 3 width. I know it's 4 feet wide, so I'm just going to take because it's a planking, I'm going to use a 1/4 section planking. So if I use 1/4 section planking, I'm going to say, okay, 50 feet times 1 feet, and that gives me 50 pounds per foot. So this is going to come out here 50 pounds per foot for the loading, and we know the span is 7 feet. Now, you all seen this, we talked about this a lot of time, bending moment. And you know, based on a bending moment formula, our bending moment comes out to, let me go over here, M is equal what? Can you remember? Anybody remember? It was only last semester. W L squared divided by 8. That's a bending moment for uniform distributor loaded beam. In our case, it's going to become 50 pound per foot times 7 by power 2 and divided by 8, and that comes out to I got it 306.25 306.25, and that's going to be a foot pound. So now I'd like to convert this to an inch pound because we're dealing with inch here. So that's going to be, if you multiply that by 12, it's going to become 3675, or same as 3675 inch pound. You remember the when we're talking about bending moment and we talk about section module, and we said, okay, the bending stress is equal what? You remember that? It's M divided by S, okay? And, or we can say S is equal, for rectangular shape, we always said for rectangular shape, S is equal what? BD squared divided by 6, and this being D and B. Now, we were told for Douglas Fair, the FAB, the bending stress is equal 1000 psi. Now remember, this is 1000 psi. So we're working with OSHA, and OSHA says you got to use safety a factor of 4. So your safety factor, or FS, whatever they call it, supposed to be 4. That means your bending stress capacity is going to reduce. It's going to be 1,000. So your FB going to come out to 1,000 divided by 4, which is 250 pound PSI. What does it mean? It means you're going to design this planking, but your limit is 250 pound per square inch. That's a limit. We know in reality the limit is 1,000 pound. 1,000 going to break it. But because OSHA has a huge safety factor, they say, no, you're going to make it, divide that by 4, and your limit is, the capacity is 250 pound per square inch. So that's what we're going to design based on. So I'm going to come in here. It says, okay, F is equal M divided by S. We knew that. And which is equal, that is 250 equal. And M came out to become 3675 inch pound. And divided by S. S is a BD squared divided by 6 in a rectangular shape. So instead of S, I'm going to go ahead and write, we know the plank is 1 foot wide. We already know that part. So we're going to say 12 inch times D squared divided by 6. Because it was given use a 12 inch plank of Douglas fir. So now that equal, and D comes out to, you can do some mathematic work, which is going to become square root of 3675 divided by 500, which is equal to 2.7 inch. So now the plank for this scaffolding has to be minimum of 2.7 inch thick. So we can use 3 inch by 12 planking. That's the minimum. You can always use, depend what you have on a side. But so now that was for the decking itself. And in the scaffolding, like the picture we showed in here, let's go back to this picture. This one is good. So now we did this decking right here. Okay, and these decking are supported by a steel pipe which goes across, and also the steel column. All right, let me erase this here and I will start over again there. We have for the steel pipe A36 FAB is equal 36 KSI. However, we said, okay, we know that, but the factor safety is 4 for scaffolding. That means our FAB for this scaffolding, let's say FABS, comes out to 36 divided by 4, which is equal 9 KSI or 9,000 PSI. Same thing. So that is the bending stress value for the steel. We know the steel will fail at 36. However, for this, we say, okay, your limit is 9,000 PSI, not 36. It's 9 KSI, not 36. So now we're going to go ahead and size the bear. The bear is this right here, this pipe that's going across right here, where the planking is, right there. So that's the bear. And we're going to go ahead and we're going to say, okay, that was, the plank is 7 feet, but if you look from the other angle, that's going to be 4 feet. So if I look at it from the top, this is 7 feet and that's 4 feet. Now we're going to look at here from this angle. And we're going to look at that angle, so we're going to say, all right, this is right here. That's my load. And this is 4 feet. What is this load right here? Remember the turbidity width we talked about before. So the turbidity width of this, it's going to be that 7 feet. in this 4 feet. So we're going to have 50 pound per square foot. Multiply that by 7 feet, and that will give you this came out to be 350 pound per foot, and we said FAB came out to 9,000, and now we're going to calculate the moment. So the bending moment for this one here is WL squared divided by 8, and that is came out to be 350 pound per foot. So I got 350 times 4 square, because that's 4 feet, and divide by 8, and that will give me 700 foot-pound. And multiply that by 12. I don't know what it comes out to, but make it that doesn't work.
8,400, Professor.
8,400? 8,400 inch pound. Thank you, Joe. So now we have that. We said FAB is equal M divided by S, and which is basically FAB came out 9,000 psi. So 9,000 psi is equal M 8,400 inch pound, and divided by S, and S we don't know what S is. So now I'm going to come in, go ahead and say okay, divide by S, and therefore S is coming out to be 0.933 inch square. So keep that in mind. We'll find that later. 0.93 inch. So when you look at the steel handbook, steel manual, and you look at the S, our S came out to 0.933. That's for the bearers. Which, if you look at right here, there's no 0.933. The nearest one is 1.01. And that gonna give me the 2.875 outside diameter piping. So the pipe is basically 2.5 inch standard pipe. If you use 2.5 inch standard pipe, your S is 1.1, so that will work. But anyway, that's where we can use this S right there. But let's go to another. I'm not using this board right. I'm gonna go over here. So now we're going to go ahead and find the minimum size of the post. So remember we talked about steel design last semester, and we said when we have a column, there's 2 ways the column can fail, right? All right, so we're going to go ahead and design the post. But one thing we have to look at before we design the post, let's see what I'm going to put on the screen for you, is we have 2 different modes of failure for the steel post. One is by buckling, and of course it can be another mode of failure by crushing, but that's not going to happen because buckling controls anyway. So one mode is by buckling failure, and the other mode is with a bending, because our axial force is not quite on a center, which we'll talk about in a minute. But we're going to focus right now on a buckling failure. We're going to design our pipe based on elastic buckling stress. And you can see the equation for it is given on a table, but we have to remember to put in the factor of safety, because this is controlled by OSHA and they require factor of safety of 4. So the equation is, so the elastic buckling stress is pi squared times margin for elasticity divided by the KL, supported length, and supported length. And we talked about this in column design, so I'm not going to explain this. Divided by radius of gyration. This is very important. And then square it. However, this is the elastic buckling, but in this case, we got to go ahead and add factor safety because we're doing a per OSHA's rule and regulation. So we're going to go ahead and go to table 114 of the ASCE steel manual and select 1.5 pipe, 1.5 inch. We're going to select this, and we're going to use a trial and error to find out if this is work. If it doesn't work, we're just going to go ahead until we get the right pipe. So let's calculate this anyway, see what this comes out to. Pi is pi, and E is a 29,000 KSI, or 29 million PSI in this case, and divide the whole thing by KL ratio. We said it was 3 floor. The posts were 3 floor, and it was 9 feet, 9 feet, 9 feet each. So we're going to say, okay, and also we're going to assume this is a pin. So our effective length is K is equal 1. And we're going to say, okay, 1 times 9 feet. Let's make that to an inch, divide by 12, and divide the whole thing by R. The radius gyration for 1.5 pipe, which we wrote down, it was 623. And let's just square the whole thing, and don't forget the factor safety is 4, and therefore our elastic buckling stress comes out to 2,381 psi. So this is our allowable stress. Remember, we said at beginning the Fy, let me write this over here, the Fy for the pipe was 36 KSI, or 36,000 PSI. Okay, and then adding a safety factor became 36 divided by 4, which became 9 KSI. And that is the yield stress, allowable yield stress for that. But because buckling control, now our allowable stress is going to be 2,000 instead of 9,000, 2,381 PSI. And we're going to use this to design it. So therefore, we're going to say, okay, if that's my stress, I'm going to equal that to P allowable, and divide that by the area and see what they come out to. We know if we have 1.5 inches, and then so we're good. So we're going to go ahead and say, okay, I'm going to write down here, 2381 is equal P, and divide that by the area. Area for this came out to be 0.799, and therefore P allowable that we're going to be able to use is equal 1902. I'm going to compare this to the applied load. The applied load came out to be 350 pounds per foot. So the reaction on each one of these pipes will be what? You remember this from, just look at the manual. That's a WL divided by 2, which is 350 times 4 divided by 2, and that is equal 700 pounds. So each one of these is 700 pounds. So I'll go 700, 700, 700, that's come 20. There's 3 floor, and 3 times 700 is 2,100 pound, and therefore this number is less than 2,100 pound. What does it mean? It means that the applied load is bigger than our allowable load, or based on allowable stress. So this is a big no good. So the size that we selected as a trial and error, 1.5 inches, is not good. That's not a problem. So now we're going to go ahead and use the next size, and we do all the same again, see what's going to happen. I'm going to erase this board. Don't go anywhere. All right, let's select a 2-inch size pipe this time, 2-inch standard size, and based on table 114, we're going to get all those information, which is our radius gyration comes out to 0.787. The area is going to come out for 107. I think that's all I need from here. So I'm going to use the same formula here, and the only thing is different, this one right here, and that's going to be 787, and rest of them is 9 feet. Nothing changed there, and therefore my allowable stress bending, allowable buckling stress are gonna come out to 3,800 psi, which is equal P allowable divided by area, and therefore it's gonna be my P allowable come out to 3,800 times the area, which is 107. 107, and that's gonna come out to 4066, which is bigger than 2100, and we know now that it's good. All right, so now we checked it. Remember we said there's two different ways this post can fail. One was the elastic buckling, which this way. So we gotta go ahead and check against the it's like a bending. The reason is because take a look at these two markers I got on my hand. This is the post, and because this is the post and the bearer is connected like that, okay, it's connected like that. So I'm going to turn it like that. So see that? It's connected like that. Therefore, that means the post, another color, the post is like this, and then you have the bearer like that. So the load is going to be like, you know, there's going to be a distance here. We've got to worry about this distance. So let me erase this, and we talk about that. Second way is because we might have a force in here, force 2, this can cause a bending stress in addition to axial stress. So if you say this is a P1 here, and this is my P2, and a P2 created bending stress. And remember the equation for bending stress, what was it? MC over I, or M divided by S. And let me just write it here so you remember it. Bending stress was MC over I, or same as M divided by S. And therefore here we have that P2 times L, that's equal your moment, divided by S, and plus this. So let's go ahead and figure this out. So we're going to calculate the this distance, which is half of the outside diameter. This from here to here basically is half of outside diameter is plus half of outside diameter of the bearer. That's the post, that's the bearer. And we said this was a 2-inch and this was 2.5 inch. So going back to the table 114, we can get all the dimension. In this case, E is equal 1/2, and outside diameter came out for that one 2.375, plus outside diameter for the bearer came out to be 2.875, and this whole thing gonna come out to 2.625. So this is equal 2.625 inch, and then we're going to calculate our stress. It's come out to our P1 we calculate become 2100. So 2100 divided by the cross-sectional area, and the area we said it was 1.07 plus P2. P2, it's this right here. That's reaction, which is 700 pound plus 700 times 2.625, and divided by section module for this. The S for this pipe came out to be I think 0.561. 0.561. Let me double check that. So that comes out to total, it's going to come out to 5238 psi. 5238 psi. Okay, so this came out to 5238 psi. That's allowable. No, this is a bending stress due to our load. So the allowable bending stress due to our load, we said it was 9,000 psi, remember? So that's allowable bending stress. Therefore, we're going to say, okay, 5238 psi, which is our bending stress based on the load, is less than the allowable that we calculated was 9,000 psi, and we are good. I hope you liked it. If you do, give it a thumbs up. Thank you.